I'm Adrien Douady. My entire life's work in mathematics was centred on the complex numbers. My contributions helped to advance both algebraic geometry and the theory of dynamical systems. Complex numbers have a long history. You see here on the left Tartaglia and Cardano, mathematical pioneers who lived during the Renaissance. On the right, Cauchy and Gauss, who consolidated the theory during the 19th century. Complex numbers are not really as complicated as the name might lead one to believe. At first, they were called impossible numbers. Even today they are still sometimes called imaginary. Well, it's true, it does take a little imagination. Yet today these numbers are everywhere in science and are not really mysterious anymore. In particular, thanks to them, one can construct beautiful fractal sets, something I worked on a lot. I even produced a film, The Dynamics of the Rabbit. It was one of the first animated films in mathematics. Let me begin by explaining the complex numbers on the blackboard. Mathematicians just love writing with chalk. You'll see in a minute that my ruler, this set square and protractor, behave rather oddly sometimes. Let's draw a graduated line on the blackboard. One of the most beautiful ideas in mathematics is to link geometry to algebra. This is the starting point of algebraic geometry. Just as we can add numbers, we can add points. Here is a red point on the line and another blue one. Let's add these 2 points. We get the green point. 1 plus 2 equals 3. When the red and blue points move, the green point, which is the sum, must move too. More interesting still is multiplication of points. Let's look at multiplication by -2, for instance. It transforms the point 1 into the point -2, of course. And if you multiply again by -2, you have to do the same thing. Change sides with respect to the origin and double the distance from the origin. You get 4, of course. If we multiply twice by -2, we have multiplied by 4. Multiplying by -1 is very easy. Each point is sent to the symmetrical point with respect to the origin. In other words, we do a half turn, a rotation by 180 degrees if you like. When we multiply a number by itself, the result is always positive. For instance, if we multiply by -1, we make half a turn, so that if we do it one more time, well, we come back to the initial point. This is why -1 times -1 is equal to +1. Simple enough. You see, for instance, that multiplication by -1 sends 2 to -2, and that if you multiply one more time by -1, you come back to 2. Obvious, isn't it? Therefore, there is no number which, multiplied by itself, yields -1. Another way of saying this is that -1 has no square root. But of course we are underestimating the inventiveness of mathematicians. At the beginning of the 19th century, Robert Argand had a really great idea. He said to himself, since multiplying by -1 is a 180-degree rotation, its square root is a rotation by 1/2 of 180 degrees, 90 degrees. If I do 2 quarter turns one after another, I end up doing a half turn. The square of a quarter turn is a half turn, hence -1. It's easy when you know how. Argand decided, therefore, that the square root of -1 is represented by the point which is the image of 1 by a 90-degree rotation. But of course this forces us to leave our horizontal straight line, since we have just agreed to associate a number to a point in the plane which is not on the line. As this construction is a bit strange, we say that this point, the square root of -1, is an imaginary number, and mathematicians denote it by I. But once we have the courage to leave the line, everything else is easy. We can represent 2i, 3i, and so on. Each point in the plane represents a complex number, and conversely, each complex number defines a point in the plane. Points in the plane become numbers in their own right. These numbers can be added, just like usual numbers. Look at the red point, which is the point 1 plus 2i. Let's add 3 plus I, which is the blue point. Well, you add them just as school children do. That gives us 4 plus 3i. Geometrically, this is just addition of vectors. You see that it's no problem to add complex numbers. Much more interestingly, these complex numbers can also be multiplied, just like real numbers. Let's see. We know how to multiply a complex number by 2, for instance. 2 times 1 plus 2i gives 2 plus 4i. Geometrically, multiplying by 2 is easy. It's just scaling up by a factor of 2. If we double the red point, we get the green point. Multiplying by I is not difficult either, since we know that I corresponds to a quarter turn. In order to multiply 3 plus I by I, we just have to rotate by a quarter turn. We get -1 plus 3i. Not so complicated, these complex numbers. And finally, we can multiply any two complex numbers with no problem whatsoever. For instance, let's try to multiply 2 plus 1.5i and 1 plus 2.4i. We proceed as usual. We first multiply by 2 and then by 1.5i, and we add the results. Therefore we get which is -2 plus 4.8i minus 1.5i plus 3.6i times I. But I squared is -1, since we invented I for this purpose. So we get -2 plus 4.8i minus 1.5i minus 3.6. And tidying up, that gives us -2 minus 3.6 plus 4.8i minus 2.5i, giving us in all minus 5.6 plus 3.3i. There you are. We know how to multiply complex numbers. In other words, we can multiply points in a plane. That's amazing. We thought that the plane was dimension 2, since 2 numbers are necessary to locate a point. And now I'm telling you that 1 number is enough. Of course, we changed our numbers, and now we are dealing with complex numbers. It seems the right time to define 2 notions, the modulus and the argument of a complex number. The modulus of a complex number z is just the distance from the origin to the point that represents z in the plane. Let's use the ruler to determine the modulus of the red point, which is 2 plus 1.5i. Let's see, it measures 2.5. The modulus of 2 plus 1.5i is therefore 2.5. For the blue point I get 2.6. And for the green point, which is the product of the 2 points, I have 6.5. As a rule, the modulus of a product of two complex numbers is just the product of the moduli of the two numbers. The argument of a complex number is measured by the angle between the abscissa axis and the straight line joining the origin to the point. Here, for instance, the argument of the red complex number is 36.8 degrees. The argument of the blue point is 112.6 degrees. And for the product, the green point, we get 149.4 degrees. That is the sum of the arguments of the two numbers. When we multiply two complex numbers, moduli are multiplied and arguments are added. Let's finish up our first encounter with complex numbers with the stereographic projection. Consider a sphere tangent to the board at the origin. Using stereographic projection, to each point on the board, that is, to each complex number, corresponds a point on the sphere. Only the north pole of the sphere, I mean the pole from which I'm projecting, has no complex number associated to it. We say that it corresponds to infinity. Therefore, mathematicians say that the sphere is a complex projective line. Why line? Because one needs only one number to describe its points. Why complex? Because this number is complex. Why projective? Because we added a point at infinity using the projection. Aren't mathematicians strange when they try to tell us that the sphere is a straight line?